Hey guys, and welcome back to another video on the channel. In today's video, we're going to be taking a look at question 6 from the QCAA External Exam for Physics 2021, Paper 2. Now, you would notice on the channel, I've started splitting up all the questions into individual videos. So if you only struggle with a certain type of question, you can go watch that exact question in a video by itself. It also allows me to go into a bit more depth on each question, rather than a full exam video taking ages, like an hour or 2 hours maybe. Now, in saying that, they're still up on YouTube. The link is in the description below. If you guys need a physics external exam bundle pack, the link is in the description below, so go get your downloads. But otherwise, let's get straight into question 6. And if you have questions at all, just leave something in the comments and I'll try my best to answer it. So question 6, the diagram shows the magnetic field lines inside a solenoid carrying a current of 2 amps. And you can see it's not to scale here, and we can see the direction of the current. Now, this is just assuming it's conventional current, okay? Always assume it's conventional current, okay? And they will tell you if it's not, okay? Conventional current's the flow of positive. Calculate the number of turns per meter that would produce a magnetic field strength of 300 microteslas at the point P. Okay, so first of all, we've got to understand which formula we're going to be using. So in magnetism, you've got access to this formula here. So the magnetic field strength is equal to the permeability of free space times by the number of turns per meter times by the length. Okay? Oh, actually, no, it's not the length, it's the current. Someone's written that really funny. Times by the current. Okay? Now, the reason why we're using this formula here is because you're given this in your data sheet here. They've given you the magnetic field strength right there. And they've also given you the current, and they're asking you to find out the number of turns per meter, which is literally that guy there in this formula here. Now notice they've given the magnetic field strength with a thing attached to it, okay? Whenever you see that, that represents micro, which is a prefix for 10 to the negative, I think it's -6. Yes, it is. So here when they've said the magnetic field strength is this, 300 microtesla, what they've actually meant is this, 300 times 10 to the -6 Tesla. Okay? So here we can rub that out. Actually, I don't know why we rub that. We need that. Okay. So here, let's just list what we have. So we have the magnetic field strength, which is 300 times 10 to the -6 Tesla. We have the permeability of free space. Now, I think in the data sheet, they just call it magnetic constant, which is 4 pi times 10 to the -7, and we don't worry about the units just yet. And then here we've got given the current as well, which is 2 amps. So here all we've got to do is rearrange this formula. So we'd move both of these guys onto the other side here to get it as the subject. So in order to do that, we have to divide both sides by the permeability of free space and the current. So we have B over that there times by the current equals number of turns per meter. So here, number of turns per meter is 300 times 10 to the -6 Tesla over 4 pi times 10 to the -7 times by 2. Then we can chuck that into our calculator. So we've got 300 times 10 to the -6 over 4 shift pi times 10 to the -7 times by 2. So this gives us roughly 119.36. Now what do they say here? Calculate the number of turns per meter, and they haven't asked us to round it to anything, so we could probably just say, you could probably just put 119. Now it'd be turns per meter, so in this case here you can just go turns / meter roughly, okay? Now, let's take a look at B. Determine the direction of the magnetic field produced by the solenoid. So here, we can work this out using the right-hand rule. Now, a lot of people don't really know how to do this that well. So they'll get this first bit, but they'll lose this mark down here. So there's only one right-hand rule you really need to know, okay? Now, excuse me while I draw a really bad right hand here. So, this is your right hand, or a right hand. Your thumb is always the direction of your conventional current, or the velocity, okay? Your fingers represent the direction of the magnetic field strength. And then your force is perpendicular to your palm. Now, in this situation here, all we need is this and this. So here, if we look in the solenoid here, we can see the current is going like this through the solenoid, like so. So here, all we have to do is go up to one of these guys here. and you have to point your thumb in the direction of the current, which would be downwards, and curl your fingers around the bar. Now, your fingers will be curling around like this. Now, if you do that with all of them, that means the current, like the direction of the magnetic field, has to be going this way, because no matter where you place your fingers, the tips of them will always be pointing in that direction if you extend it out of a circular motion. So, for example, if I were to draw it here, your things would be going around like this. So on this side here, it'd be coming out of the page, and then on this side here, it'd be going into the page. So if we treat it like this here, so on this side here, this would be coming, quote unquote, out of the page towards you, and this would be going into the page here, which means the direction would be going from left to right. Now you can just draw an arrow there, so as long as you draw it in this direction here, that should be fine as well. And that's how you do question 6. If you have any questions about that, leave something in the comments below. If you guys need a physics external exam bundle pack, the link is in the description below. But otherwise, I'll see you guys in the next video.